Hi, in this video we are going to continue on the topic chemical reactions and energy. And now we are going to talk about this topic, standard enthalpy change of reactions. Now before we talk about, when we introduce this topic, we say that we are interested in finding the energy change of a reaction. So if the reaction release heat, we want to know how much heat it can release, all right? That is very important because, for example, if I use one of the examples that we have discussed before, like this one, the hand warmer. So, the reactions that is involved is this one, a very simple redox reaction. And let's just say in order to have a functional heat pad, it needs to provide 1000 kilojoule. Okay, this is an example. It has to provide 1000 kilojoule. Then we are so interested in knowing that, okay, how many grams of iron do we need in order to provide 1000 kilojoule? Okay, so we want to establish the relationship between the quantity of the reagent as well as the total amount of energy change it is involved in. In this case, we want to know how much gram of iron is required to provide 1000 kilojoule of heat. Okay, we can obviously perform experiments to find out. However, even though we have a very good experimental design, even though we have carried out the experiment with no error, but we have one question in our mind, is that is your finding really relevant, really valid? Now, what do you mean by relevant? What do you mean by valid? So basically means if you are able to find out, say for example, 100 gram of iron is able to give us 1000 kilojoule. So if I am doing the same thing, if I am having 100 grams of iron, do I actually get 1000 kilojoule? Like, this is my question. So of course, it depends on a lot of situations, a lot of factors. For example, when you do this experiment, are you doing this at room temperature, or are you doing it at a higher temperature or a lower temperature? Because a reaction may take place a little bit different at different temperature, and obviously it may give us different amount of heat. Okay. Also, I'm interested in knowing that whether you carry out the experiment at room pressure. Like, pressure again may affect the extent of reaction. And also, is your iron pure? Are they in solid state? If I do it with a liquid iron, for instance, would I also give the same amount of heat as I react with oxygen? Like, all of these different conditions, and there should be even more, are important because I want to know whether your data, your finding is relevant, is trustable. Okay, so that's why when people are finding the energy change of a reaction, of a process, they have set up a list of standard conditions, standard requirement, of which we have to follow. So that's why over here in this topic, we have something called standard enthalpy change. So enthalpy change, basically energy change, but you see the word standard here. That means this particular energy change is found under a certain standard conditions. So therefore, we want to emphasize on what are the standard conditions that we must comply with as we are finding the enthalpy change, so that our data, our result is relevant, is reliable. Okay. Now here are 4 standard conditions. First of all, temperature. Temperature must be maintained at 25 degrees Celsius or 298 Kelvin. For pressure, we are looking for atmospheric pressure, so 1 atm. For concentration, so if your reaction involves solution, then we expect the solution to be 1 mole per dm cube. But this is only applicable for reactions that is involving solution. So just now, this one, well, we are not concerned about the concentration because they are not aqueous solutions. And lastly, standard state. So we say that all the reactants, all the products, they must be in standard states. Now, what do you mean by standard states? So standard states basically means the most stable physical state at the given condition. So, for example, if we talk about iron just now, iron should be a solid at room temperature, right? So, iron in liquid form is not considered as standard state. So, what about oxygen? So, oxygen is obviously a gas, but oxygen has several allotropes, right? Allotropes means they are the same element, but they have different structure. For example, oxygen, we have O2 and O3. So both of them are oxygen elements, but of course, the most stable form would be oxygen. So if the reaction takes place between iron and ozone, then the result is irrelevant, is not reliable. Okay, so that's the idea. These are all the standard conditions. So down here, basically substantiate a little bit on the allotropes. Okay, for carbon, of course, we are looking for graphite. For phosphorus, we're looking for red phosphorus. For oxygen, we are looking for diatomic oxygen instead of ozone. Okay? Remember, we must stick with the standard state when we want to determine the standard enthalpy change. Okay? Now this one is just, actually you know that when diamond is converted into graphite, this reaction is actually exothermic. Okay, so when diamond is converted into graphite, actually it releases heat. But of course, you are not able to detect the heat because the reaction is so slow that even it proceeds, it takes like millions of years, or if not even more. Okay, so this is just something extra for your interest. Now down here, now this is the part where you have to actually memorize a lot of things, because for energetics or for this topic, we have very strict definition on several terms, and very often the question will ask you to define. So you must pay extra attention to the use of terms and the definition as well. So I'm going to break it down to you. First of all, standard enthalpy change of reaction. Now look at the symbol. Very often we will use the symbol to represent. So delta H, delta means change, H means enthalpy, and this one, naught, we say delta H naught. This naught basically means standard. So if you see this one, that means the reaction must take place under all this set of conditions. If you don't have this naught, that means it just take place at a certain condition, may not exactly be the standard conditions. So here we say that it is the enthalpy change when number of moles of reactant represented by the equation react completely under standard conditions. Now, basically, simply put, the enthalpy change of a reaction according to the chemical equation under standard conditions. Okay, may not be very important, but let's have a look at these examples. So the first one here, you see, hydrogen reacts with oxygen to form water, right? So this equation, it has an enthalpy change, but does it consider as standard enthalpy change? Well, no, because you see, water is in gaseous state, but at standard condition, 25 degrees Celsius, H2O should be a liquid. So that's why it is not considered as standard enthalpy change of reaction. Like this one is not the standard enthalpy change of reaction. Okay, so that's why in this topic, in this whole chapter, you have to actually use or indicate the physical state of all the chemical species, because you see, if you do not indicate the physical state, we have no idea whether it is a standard condition or not, or standard enthalpy change or not. Right, so down here, H2 reacts with O2 to form H2O. Now this time it is liquid, so it is considered as standard enthalpy change. And you may notice that liquid and gas, they actually have different enthalpy change value. Now here, if you can follow, then it will be very good. You may notice that this equation is more exothermic than this equation. And why is that? Actually, the reason is because this one obviously is an exothermic process, so it releases the heat. But part of the heat released is used to boil the liquid water into water vapor. So that's why if you want to use this equation, then the enthalpy change will be less exothermic. Okay? This equation is less exothermic than this one because part of the heat released is used to boil the liquid water into steam. Okay? Now, down here, you see this equation is basically the half of the second equation, right? And you notice that the standard enthalpy change will be exactly half of this one. Now, that makes a lot of sense because if you produce 2 moles of water, then it is like releasing this quantity of energy. When you are producing half the amount of water, then you will as well release half the amount of energy. That makes a lot of sense. So you may realize that based on how we put down the equation, it has a different enthalpy change value. So that's why here we say that we have to follow the chemical equation, follow the number of mole of reactant and product that is shown by the equation. Okay? Now here, the unit for standard enthalpy change is kilojoule per mole. Pay extra attention to the unit. Okay? Because very often, a student may miss the unit and you will have 1 mark deducted. Okay? So that's the idea. Okay, on the right-hand side here, we have something called thermochemical equation. Now, what is the difference between chemical equation and thermochemical equation? Now, there are mainly 2 differences. One is that for thermochemical equation, you must show the physical state. You must show the physical state. And secondly, if you have the enthalpy change, you need to show the enthalpy change on the right-hand side of the equation. Okay, so you must have all these physical states. So if the question asks you to put down a thermochemical equation, you must include all the physical states. Basically, in this topic, in this chapter, just include all the physical states for all the chemical species. Okay. Now down here, you see 1, 2, 3. So these 3 energy terms, very important. So you can like put stars, put stars, put stars here, okay? Please memorize all these definitions because very likely that one of these 3 will be asked in the exam, okay? So let's have a look. So the first one, standard enthalpy change of neutralization. So neutralization, acid reacts with alkaline, right? Now, I will underline all the keywords that is necessary when it comes to the definition of this term. So first of all, it is the enthalpy change. Now don't miss this one. If you forgot to put down it is the enthalpy change, you lose all the marks. Okay? It is the enthalpy change when 1 mole of water is formed from neutralization of an acid and alkaline under standard condition. Basically the entire sentence. Okay? Now, here we want to find out basically the enthalpy change of a neutralization reaction. So when we have neutralization reaction, no matter what acid, what alkaline, we must produce water as the product, one of the products. So here we try to define such that 1 mole, the enthalpy change when 1 mole of water is formed from a neutralization reaction between acid and alkaline. Not base, you cannot put down base here. Okay, alkaline, under standard conditions. Okay, so this is an example, of course, because it produced 1 mole of water. Okay, now you pay attention to one thing. You may ask, hey, can I put down, for example, like this one? Okay, can I put down this one as the equation substantiating the definition? The answer is no, this is not correct. Hey, why is that? Because here. Because, like I said, the definition stated that only 1 mole of water is formed. So this equation is not acceptable because this equation is showing 2 moles of water. Hey, so how do we reduce 2 moles into 1? Of course, you will have to halve the total equation by 2. Then just halve the equation. So you will mix it into 1. So this is not correct. So the correct version would be, now this is correct. Okay? Now you see, we don't really have, right? We don't really have a fraction number or decimal number in the equation. Very often we will multiply by 2 so that it becomes a whole number. Now this is the case for chemical equation. But for thermochemical equation, for this topic, we must strictly follow the definition. If it says 1 mole, then you must have 1 mole. Okay? So yeah, basically we have to follow the rules and everything would be fine. Okay? All right, and one more thing, exothermic. All the neutralization reaction, no matter strong acid, strong acid, weak alkaline, blah, 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 even weak acid with weak alkaline, they are always exothermic, okay? Now, the symbol here, so delta H not neutralization, okay? Delta H not neutralization, that is okay, right? The not here, you can put it here, you can put it here. I think it would be best if you put it here, okay? Now, the second definition, standard enthalpy change of formation. Now, here, it is the enthalpy change. Let me use another color or highlighter. Okay, it is the, again, enthalpy change. Don't miss out this one. It is the enthalpy change when 1 mole of compound in a standard state is formed from constituent elements in the standard state under standard condition. Now, you see so many keywords. So that's why you really have to pay more effort in memorizing the definition. Now here, now formation basically means we form something. We form a compound. We form a compound. So, you know, the compound must consist of at least 2 different elements, right? At least. So actually we form the compound from its constituent elements. Constituents means composition. So basically, for example, if the compound is carbon dioxide, then it is formed from carbon element and oxygen element. So these are the constituent elements. But the constituent elements must be in standard state. So that means, for example, if you have carbon dioxide, okay, just now I talked about carbon dioxide. If you want to form carbon dioxide, you can't just put down C plus O, 2 oxygen atom and form CO2. This one is wrong. So you see, according to this equation, we have carbon, we have oxygen element. However, this thermochemical equation is not acceptable, not only because we don't have the physical state of all the species, but most importantly, it is the oxygen, right? Because oxygen, the constituent element, must be in their standard state. So oxygen atom is obviously not the standard state. It is obviously not the most stable form in room condition. So that's why this is not acceptable, and the correct version must be carbon, O2, CO2. And this is acceptable, okay? And here, carbon, solid, we are implying graphite actually. So it's obviously not diamond, okay? So here, another example here is methanol. If you want to form methanol, so the equation would be carbon, solid, reacts with 2 moles of hydrogen gas and half mole of oxygen gas. 2 mole of hydrogen gas give us 4 hydrogen atom, and half mole of oxygen gas give us 1 oxygen atom. And pay attention that methanol as an alcohol is liquid at room condition. Okay, so that's the idea. All right. Now here, you see, what about the formation of elements? Now, what if we form an element? Now, let's just say I want to form, for example, I want to form nitrogen, okay, form nitrogen. So N2 gas. Okay, so I want to form nitrogen. So according to the definition, formed from its constituent elements. So nitrogen is made by nitrogen, and nitrogen must be in standard state, so it must be N2. Okay, now you realize that, hey, is there any difference between reactants and products? There is no difference at all. So you don't expect it to be a reaction. There's not even a reaction, right? So that's why the standard enthalpy change of formation of all the free elements basically means elements, okay, at their standard states are all zero. So this one is very important. Okay, the standard enthalpy change of formation of free elements are simple, zero. Okay, so that's the idea. This is the formation. Now, for standard enthalpy change of formation, it could be exothermic, it could be endothermic. We don't have. It doesn't look like neutralization, which is always exothermic. Formation, it could be exothermic, it could be endothermic. Now down here, combustion. So should be quite straightforward. So when you burn something, okay, this is the enthalpy change when you burn something. So it is the enthalpy change when, again, 1 mole of substance is completely burned in oxygen, okay, under standard conditions. All right. So here, this time we are burning 1 mole of a substance. It could be the fuel, it could be some other element, okay? And when you burn it, you must burn it in oxygen, and the combustion must be complete, because complete and incomplete combustion has different enthalpy change, obviously, and it's under standard conditions. And for example here, if we want to burn here butane, so it reacts with oxygen to form carbon dioxide and water. Now you may notice, hey, sir, why is it like 13/2? Can we just multiply the whole equation by 2? Of course not, because this time you have to pay attention. 1 mole of substance, and that 1 mole of substance, in this case, it is the butane. So we must fix the mole ratio, the number of mole of butane being 1. So that's why the oxygen, even 13/2, is ugly. We have to put it this way. Okay, so that's the idea. Now for combustion, it is always exothermic. Always exothermic. All right. Now, and one more thing. Even though we put down standard conditions, actually temperature is not involved as one of the requirements. It's not considered, because that makes a lot of sense. When you burn something, it has to be higher than 25 degrees Celsius, right? So for standard enthalpy change of combustion, the temperature requirement is actually withdrawn. But for simplicity's sake, or as our usual habit, we will assume that the reaction takes place at room temperature. In other words, the standard condition here only concern about room pressure, okay? Now, also one more thing you may notice. For all 3 definitions, we have a very strict requirement regarding the quantity. That makes a lot of sense, because just now, at the beginning, we say that we are interested in finding the enthalpy change which are reliable, which are able to serve as a valid reference. So, of course, the quantity of the chemical involved is important, because if we only know that it can produce like negative 2,878 kilojoule, then how much fuel do we need to release that kind of heat, right? So the quantity is important. So we need to specify the quantity for each enthalpy terms. Now, you may notice sometimes we will specify 1 mole for one of the products. Sometimes we will specify 1 mole for one of the reactants. So that's why you have to pay attention. For neutralization, 1 mole is concerning about the water, which is the product. For formation, 1 mole is concerning about the product being formed from its element. But for combustion, we are focusing on 1 mole of reactant being burned. Okay, so make sure you know which chemical species must be fixed in 1 mole quantity. Okay, now so that would be all the important things about this standard enthalpy change. Now next page here we have 2 pages of practice question. So again, you know the tricks. You can pause the video and try to go through this question. But here I just want to do one demonstration for question 2a here. It says, write an equation to represent the following thermochemical process. So the equation must be a thermochemical equation. I just want to do one example. So here, standard enthalpy change of formation of benzene, okay, delta H naught F and then benzene. So it must form from its constituent elements. So it must come from carbon and hydrogen, C6H6 liquid. Okay, make sure you include all the physical states. And this one must be fixed in 1 mole. So that's why you must have 6 here and then 3 here. And that should do it. And you don't have the enthalpy change given, so you don't have to put down here. Okay? So this is what I expect you to do. Now, please pause the video and go through all these 5 practice questions and then resume the video and check the answers. Okay, let's have a look. Okay, which one requires standard condition? Of course, 1, 2, 3 require standard conditions, right? Now, which one is always exothermic? So like I said, only neutralization and combustion, okay? 1 mole of reactant. So this one must be combustion because for this 2, the product is fixed as 1 mole. Here, 1 mole of product formed, so that would be this 2. Okay? Now here, O2 become O3. So this one belongs to which? Now, obviously, it is not neutralization. We don't have any acid and alkaline. Is it combustion? So, well, when you burn oxygen with oxygen, it doesn't really look like combustion at all. So actually, this one is the standard enthalpy change of formation of ozone. Because ozone, it is formed from its element, which is oxygen as well, but this is O2. So this is actually the standard enthalpy change of formation of ozone. Okay. Down here, this one, H plus and OH minus form H2O. This one is definitely neutralization. Okay. Now you may say, hey, is it formation of liquid water? Of course not, because the standard enthalpy change of formation of liquid water should be H2 gas reacts with half mole of O2 gas, right? So this is not the case. Now here, carbon reacts with oxygen to form carbon dioxide. So you may think that, oh, this should be formation, right? Formation of carbon dioxide gas from elements. But if you are smart, you realize that it is also considered as the standard enthalpy change of combustion of carbon, right? When you burn carbon, you react with oxygen and you form carbon dioxide, right? So sometimes you may realize that one thermochemical equation could be used to represent more than one enthalpy terms, okay? This would be an example. And lastly, this one. This one, actually, you may think, oh, should not be neutralization. We don't have any acid and alkaline. Even though it forms a salt, but neutralization emphasizes on the formation of water, so it is not this one. Is it combustion? Definitely not. You can't see any oxygen, right? So is it formation? Now you may take the formation because it really forms a sodium chloride, and you know that sodium chloride comprises of sodium ion and chloride ion. But like I said, the definition stress on the formation of compound from its elements. Are these elements? Obviously not. These are ions. So that's why actually here we can't tick any one of these boxes. Okay? Okay, so down here I did the first one already. So here, standard enthalpy change of combustion of propene. So we have C3H6, which is a gas, reacts with oxygen, which is also a gas, to form carbon dioxide, gas, and water, liquid. Now pay attention, this one is liquid because this is the standard state of water. Okay. So here, usually we'll put down 3 and then 3 here, right? And 3 times 2 equals to 6 plus 3 equals to 9. So usually we will multiply the whole equation so that we got 2, 9, and then 6, and then probably 6 as well. But like I said, we must fix this one as 1 mole. So that's why we actually have to do it this way. 3, 3, and then over here, 9 over 2. Okay? Now here, standard enthalpy change of neutralization between nitric acid and barium hydroxide. So nitric acid, HNO3, AQ. Barium hydroxide, AQ. To form BaNO32, AQ, as well as water. Okay? Now, of course, when you try to balance the equation, usually we will put down 2 here because we see we have 2 nitrate ions. But if you put down the 2 here, you may later on need to put down the 2 here. Okay? Because then we will have 2 H2 plus reacts with 2 hydroxide ion, obviously forming 2 moles of water. But remember, for neutralization, we must form 1 mole of water only. So that's why in this situation, we actually have to halve this 2, okay? Okay, for D, standard enthalpy change of combustion of methanol. You burn methanol, so CH3OH, liquid, burn it, so O2, forming carbon dioxide and water. Okay? So balance the equation. So 1 here, no need to change. So hydrogen, we have 2, for water, we have 2 of them. And lastly here, we have to do like 3 over 2. Don't forget we have oxygen in the hydroxyl group. So here on the left-hand side, we have altogether 4 oxygen atoms, same as the right-hand side. So it is balanced, and make sure this one is 1 mole. Okay? And lastly, the standard enthalpy change of formation of sodium hydrogen carbonate. Okay, so sodium, Na, solid. Hydrogen, H2, gas, we have half of it. And then carbon in the form of graphite. And oxygen, O2, gas, to form NaHCO3, solid. Now for oxygen here, we need to use 3 over 2 oxygen. Okay, so this is the equation. Okay, so next page. Question 3. So which of the following combination is correct? Okay, so the first one. This one, standard enthalpy change of formation of hydrogen carbonate. Now, formation must come from elements, but these are compounds. So this one obviously not correct. And here, combustion of hydrogen. So H2 reacts with O2 to form H2O. It sounds pretty good, but it is also not correct. Because when you burn something, you burn 1 mole of the fuel. So this one, we have 2 moles of the fuel. So that's why it's not correct. It should be H2 plus half O2 forms H2O. Okay? Now here, neutralization between sulfuric acid and calcium hydroxide. This equation is balanced. Looks pretty good, but again, not correct because here, okay, we can't have 2 moles of water. We only have 1 mole of water. So actually, we have to do like half, half, and half. Okay? And lastly, formation of phosphoric acid solid. Okay? Now, phosphoric acid, you may ask, hey, sir, should I put down AQ here? No, because first of all, I put down solid here. So it is correct. Okay? I want to form a solid phosphoric acid. And secondly, actually without water, if there is no water, phosphoric acid is a solid. Right? Now here, so formation, so you have hydrogen, phosphorus, and O2. Now phosphorus, remember, it exists as P4 rather than just P or P2. It exists as P4. Just like sulfur exists as S8. Okay, you will learn it later in the topic patterns in the chemical world. Okay. Now, so all the elements are correct. Check the stoichiometry. 3 correct, 1 okay, and 4 oxygen. So this one is correct. So the answer is D. Okay. Now question 4 here. So we have a thermochemical equation: phosphorus reacts with oxygen to form P4O10. Given that P4 and P4O10 are in the standard state, so they are already in standard state. Also, oxygen is obviously in its standard state. Which of the following is correct? It is an exothermic process. Of course, it is correct because of the negative sign here, right? It is exothermic. It represents the standard enthalpy change of formation of P4O10. Okay, now, so we have to check. Is it standard state? Yes. Is it 1 mole? Yes. Are these elements? Yes. Are these elements at their standard state? Yes. Are the stoichiometry correct? Correct. So, correct. Okay? So, yeah, just follow the rules and check every point. Okay? Now, it represents the standard enthalpy change of combustion of phosphorus, or combustion of phosphorus. So, phosphorus here is a standard state. Yes. Is it 1 mole? Yes. So, burns with oxygen. Oxygen, standard state, no problem. Forming the product. Okay? This one, no problem. Correct. Okay? So, actually, the answer is D. Again, one single equation represents 2 enthalpy terms. Now, question 5 here. The enthalpy change of the following reaction at 1 atm, 298 K, and this one is negative 200 kilojoule per mole, and it says that A and B are 2 different elements. Elements, okay? Which of the following concerned about reaction is incorrect? So this one is an exothermic process. This one is correct because of the negative sign. It is the standard enthalpy change of formation of AB gas. Now, AB is a compound of A and B. These 2 are elements. So this one, it looks pretty good for me. So this one is correct. Now, here, the enthalpy change of the reaction AB. So basically flip the equation. So as you flip the equation, actually the enthalpy change is the same. We did talk about that when we talk about the bond breaking and bond forming. Right? Imagine all the reactions are involving bond breaking and bond forming. So if the reaction like this is negative 200, and if it reverses, then all the bond forming becomes bond breaking. All the bond breaking becomes bond forming. Then, of course, the quantity will be the same, but except the sign is different. So this one is also correct. And here the enthalpy change of the reaction is the same when it is repeated at 313 K. This one I'm not sure, because this is exactly why we need the standard condition. The standard condition is because reaction may take place differently at different temperature. So that's why we have to fix it into 298 K. All right?